Let's continue with our discussion of Thevenin Norton. And we'll look at a couple of examples trying to find Thevenin voltage, Norton current, and Thevenin resistance. And then we'll wrap up with superposition, another important concept. Okay, let's see. So you're looking at this circuit, and we talked about finding the Thevenin voltage and Norton current by measuring the open circuit voltage at these terminals, and then short circuiting the terminals so that current flows through the terminals. And then the current that's flowing there, the short circuit current, is our Norton current. So then okay, so then we use Ohm's law to find RTH. Anyone remember what I said about this? I said we don't want to use Ohm's law to find it directly, because if either VOC or ISC is incorrect, then our RTH will also be incorrect. So the relationship between the three is, of course, VTH is equal to IN times RTH, right? So in order to find these three quantities, if we use just two, then the third one could also be incorrect if one of them is incorrect. So we use a third technique to find the REQ or the RTH for that circuit. Okay. Let's see. Voltage divider, we'll look at that just a little bit afterwards. Okay. First, trying to find VOC. If you want to find VOC, the open circuit voltage, what do we do? Well, we simply analyze the circuit as it is and calculate the voltage between those terminals. So how do we do that? Well, if we see this circuit, what are we doing? We are simply measuring across the 3.3 kilo ohm resistor. Actually, let's go to the other side. Let's go here. Okay, so we are measuring the voltage across a 3.3 kilo ohm resistor. My output terminals are connected directly to the 3.3 kilo ohm resistor. So if you're trying to measure on the outside of the circuit, inside, effectively, we are simply measuring the voltage across that resistor. And if you look at the resistor, what do we see? We have current that comes from here and flows through both resistors. There is no other pathway for the current to flow through. So if the same current is flowing through both resistors, what can we say about their connection? Anyone? They're in series. So if they're in series, we can apply Ohm's law and calculate the current I. Okay, we apply Ohm's law, calculate the current I. Series connection, REQ is 5.1 plus 3.3 gives us 8.4. 8.4 kilo ohms, and 10 volts divided by 8.4 gives us the current I. Once we have the value for current I, we can apply Ohm's law again to find the voltage across that resistance. That gives us 3.93 volts. And the 3.93 volts is our Thevenin voltage. Okay, that is our Thevenin voltage. That is the voltage we are measuring at the output terminals. Okay, does that make sense? Any questions? Okay. Yes. Real life examples are being asked. So real life example for this could be like a dependent source. You'd have, let's see. Have you all used the 555 timer chip in your labs? Okay. So the examples of these kind of series connected resistors in all circuits. Any and all circuits will have at least series connections like these. So this is an effective way of finding different voltages or deriving different voltages from one single voltage source. So if you ever, nowadays, of course, people don't use desktops a lot, but inside every desktop, there is a power supply or an ATX power supply, and it has multiple cables coming out, and they have multiple voltages. Okay, because every single part of the computer requires different voltages. The fans require a different voltage. The CPU requires a different voltage. Breadboards, USB, the PCI boards, the add-on video cards, everything requires different voltages. So you have different voltages going to different parts. Yet, if you look at a laptop only has one power outlet. It's 19 volts or 20 volts, and it plugs into your laptop. Nowadays, of course, it's USB-C. But if you wish to get multiple voltages from there, we apply it to a series connection of resistors. And depending on the value of these resistors, we can obtain different voltages going into our devices. So this is very common. Okay, that's the real life example. Any place where we need to have different voltages going into different parts of our circuit, use a voltage divider network. Right? Okay, let's come back to our discussion. So now we need to find ISC, the short circuit current. What do we need to do? We place a short between these terminals. Okay. If you place a short between these terminals, and then we calculate the current that's flowing in this branch. Okay. So these are my output terminals. I place a short circuit wire between them. Once I have a short circuit wire, now I'm going to calculate the short circuit current that's flowing through that branch. Now take a few seconds, look at the circuit, and tell me how has the circuit changed? What is that short circuit doing? First, look at where it's connected, and then tell me what it is doing. You figured it out? Absolutely. Because we have a short circuit in there. So the explanation is this. What is the resistance of a short circuit wire? It's an ideal wire, right? So it's 0. Now, if it's 0, anything that is connected in parallel to that short circuit is effectively redundant. Because if we have current coming out from the source, making its way down from the top, it would technically should split in two, right? It should go down two paths. But current always takes the path of the least resistance. And if one of those resistors in parallel is 0 ohms, then everything is going through there. If R is 0, current is infinite. It's the least resistance. Even if the other resistance is only 0.1 or 0.2 ohms, which is even smaller than what we can typically measure, 0 is still less than 0.1. 0 is less than 0.00001. Doesn't matter how many zeros we want, right? So technically 0 is the smallest value in that sense. And so everything goes down that pathway. Nothing goes down 3.3 kilo ohm. And so effectively, It is no longer part of the circuit. So the only thing left in the circuit is the 5 kilo ohm resistor. We apply Ohm's law once again. And you find that current. That is your Norton current, 1.96. Okay, 1.96. Does that make sense to everyone? Okay. That's an important concept to remember and retain. Okay? Anything that's connected in parallel to a short circuit is effectively removed from the circuit, because the short circuit, or anything that's between any two nodes, right? So if there's a short right there, if it's the same node, then it's effectively no longer part of the circuit at all. It's an important concept to remember. Okay, so from here you apply Ohm's law, you can find 2 kilo ohms. And in my quizzes and exams, I will state there, do not use Ohm's law to directly find RTH. Okay, but this is a way to find RTH. Okay, let's look at, come on. Okay, let's look at this first, then we'll go back to the other slide. So the method of finding RTH is by simply measuring or calculating REQ at those terminals. Okay, so there is nothing new in this. REQ is something that you, REQ is something that you've already learned in the past, that you already know how to do. So RTH is simply calculating REQ. Okay. In order to do that, we have to ensure that there is nothing left in the circuit except resistors. Meaning if there are any sources in the circuit, we have to remove those sources. We have to deactivate them. We have to reduce them to 0. Now, deactivating a source does not simply mean that you turn it off. Okay. That's not what it means. That's not what it means in this sense. Deactivating a source or reducing its value to 0 means something else. It's called deactivating sources or reducing its value to 0. So what do we do? Well, what we do is we take out the sources and we replace it with something. So we replace voltage sources with a short circuit wire. And we replace a current source with an open circuit. And I will draw out and illustrate. So let's say in a circuit, we have this. We have a voltage source connected between 2 points. We remove it and we replace it with a short circuit wire. So effectively, between those 2 points, we now have a straight line. Both those points are at the same node. If they are at the same node, the voltage between those nodes is equal to 0. So the only way to ensure that the voltage source is reduced to 0 is by shorting out those terminals. Okay. Again, these are important. This is an important concept in circuit analysis. Okay. Yes. Good question. We'll do it in just few slides. We'll actually do it right now here to find REQ, and then we'll also use it again for superposition. Yeah. Okay. So the same thing for a current source. If this is a current source, what do we do for the current source? What do we do after removing it? And so what do we need to draw in there? Nothing. So not a trick question, but it just means nothing. So replacing a current source with an open circuit simply means you remove it. That's all. And so if you have a circuit, you don't even need to draw anything. Current source is gone, so it's gone. That's it. If there's nothing else in that branch, we don't need to do anything. Effectively, that anything that was in series with the current source is no longer part of the circuit, because if it's an open circuit, no current can flow between those 2 points. If there's no current flowing, it's not part of the circuit. And this is the only way we can ensure that the current through that branch is equal to 0, is if there's no pathway for the current to flow through. Okay, so replacing a current source or reducing it simply means you remove it from the circuit. And then once you modify the circuit in this manner, the only thing that's left in the circuit are your resistors. And now we can calculate our EQ, right? So all we have left in the circuit are resistors. Then we can now calculate our EQ. And so we'll see how we can do that for the previous example, or this example. Okay. So my circuit is this. I have a 10-volt source. We have 2 resistors in there. Any questions? And I'm trying to find REQ between these 2 points, right? Those are my measurement terminals or terminals of analysis. This is where I'm trying to calculate my REQ. So this is 5.1 kilo ohm, 3.3 K. What do? We short out the place where the voltage source was connected. And we measure REQ. Okay. Did you all finish Thevenin Norton this week in the lab? Okay. So now, what do we see? Because the voltage source is replaced with a short, I can say effectively the 5.1 and the 3.3 kilo ohm resistors are in parallel. So calculate REQ. Take out your calculators. Let me know what value you obtain for REQ. 2000 ohms, yes, but tell me the decimal places. Great. 2.00357. So this is just a learning moment for everyone. So usually when I have unit prefixes like 10 raised to 3, 10 raised to 6, 10 raised to 9, I like to take as many decimal places as I can because it makes a big difference. So 2.00 kilo ohms, but in fact, the number actually is 2.003. What did you say? 357 kilo ohms. If I remove the unit prefix, what do I have? 2003.57 ohms. That 3.57 ohms could be a big change down the line in a circuit. Okay. So as engineers, it behooves us to actually be very accurate with the numbers. Okay, all right, coming back to our problem. So Req is approximately 2.003 kilo ohms. And look at the value that was obtained by applying Ohm's law. 2 kilo ohms. Okay. So now if we had calculated VTH, RTH, and IN separately, we can use Ohm's law and verify our answer. Because if one of those three quantities is incorrect, then we know where the error is. But if we apply Ohm's law directly to find RTH, then we are unable to do so. Okay. That's why we use REQ techniques to find it. Okay. Let's see. Oh yeah, Thevenin of voltage divider. So this circuit is known as a voltage divider right here. And the reason is you have series connected resistors. In a series connection of resistors, the current remains the same, or current is the same for all resistors, but the voltage is divided. And so we have what is known as the voltage division principle. Okay, voltage division. How do we derive this? Well, we have current flowing through the circuit. Is the current going anywhere except R1 and R2? Those two measurement terminals are simply wires. They're open, they're not connected to anything. So if they're not connected to anything, there is no current flowing through them. That means R1 and R2 are in series, right? So if I was to write an equation for the current I from Ohm's law, I can write I is equal to V over R1 plus R2. This is from Ohm's law. And now if I wish to find VR1, if I have I can find any other voltage in the circuit. So VR1 is what? I times R1. I is something we calculated from above. And so I can plug in I times R2. Rearrange the terms. What do we obtain? We obtain the voltage division. Oh, this is R1. Okay. All right. Let's take a pause. Let me know if you have any questions. Yes. Thank you. So what is VR2 then? Take a guess. Absolutely correct. Yep. And that, in short, is the voltage division principle. This is VR1 is equal to R1 over REQ times V. Okay. This REQ is not the same as the REQ we obtained from the measurement terminals because the terminals are different. This REQ is from the perspective of the source. Okay. So it is measured from the source terminals, not from the previous terminals. So I'm going to take a shortcut. Right? This REQ is from the perspective of the source. So it's measured from the source terminals. And from the perspective of the source, the two resistors are in series. And that's what it means to have, sorry. And this is how we apply voltage division. It's a one-step shortcut. Instead of applying Ohm's law to find the current first and then applying Ohm's law again to find the voltage, we can have a direct shortcut where you can easily calculate the voltages in a series connection of resistors. And that is voltage division. And so VTH has this direct equation. And this principle can apply to any series connection of resistors. Doesn't matter how many we have, whether it's 10 or 100 or 1,000 or a million, as long as they are all in series, this principle will still apply. Okay, it still applies. It's a quick and easy way to find the voltages across any single individual resistor. And then RTH for this is exactly the same as we saw previously. The two resistors are in parallel. So if you have a voltage divider network like this, we can easily calculate the Thevenin resistance as well as the Thevenin voltage. Okay. All right. So now let's look at how we can apply these techniques to superposition. Okay. The first two slides are information to student reading. So please read these. So it's student reading and review. Okay. Student reading and review. Okay. So superposition, that is what we're going to look at. So let's say we have a circuit that looks like this. Okay. And you're asked to find the Thevenin voltage and the Thevenin resistance. Okay, so we have multiple sources in the circuit, more than one. In this case, it's easier because it's only two. But you could have 3 sources, 4 sources, 5, 6, 7, 8, 9, 10, n number of sources. Okay, but let's say if this is a linear circuit with linear components, then the superposition principle states that if you have a linear circuit comprising of linear sources and linear components, we can break up the analysis of this circuit and analyze each piece individually at a time. Okay. That is the principle of superposition. Superposition principle states that the voltage or current in a multi-source circuit. All right. So the voltage or current that appears at any point in the circuit is a result of all of these sources working at the same time. Okay. So if you have like 10 different sources in the circuit, whether it's voltage source or current source, does not matter. Could be any combination of those. And you have n number of sources. Then the voltage or current that results at any given point in the circuit is a result of all of those sources working at the same time. And so theoretically, if we can analyze the circuit only one source at a time, and we find the voltage for every single source, we can sum it up, and that should equal our actual voltage. Okay. So superposition. Applies only to linear circuits. Okay. What we do is we break up the analysis or break up the circuit and analyze. Now, when I say break it up, it does not mean that you're removing any other component. The only thing that we are dealing with is individual sources in the circuit. Okay. So we analyze it. With only one source active at a time. Okay, analyze circuit with only one source active at a time. And take a minute to, not a minute, but a few seconds to look at the circuit, and then we'll analyze it. How many of you have heard of superposition before? Okay, great. Have you applied it before for circuit analysis? Okay. Probably physics, right? Yeah. Okay. Okay. All right. Look at the circuit. Oh, sorry. Okay, you can just speak up if I'm like too many things going on in my head. I'm doing a few things. Then speak. Linear circuit means we have linear sources like the ones we saw, and then linear components like resistors, capacitors, inductors. Mostly just resistors. They have a linear, the voltage and current have a linear relationship with each other. Okay, so if you look at this circuit, let's first look at RTH. The point is in front of you. What does it state? If you want to find RTH, all we do is we short out all, not short out, we reduce all the voltage sources and current sources in the circuit to zero. So let's redraw this circuit in a bit, right? What do we have? We have terminal A at the top, and then I have terminal B at the bottom, right? A and B. What is connected at A? If I look at the very top, if I look at the very top, I have a 10 kilo ohm resistor. Which is connected in series to a 2-volt source. Then what do I have on the far right? 30 kilo ohm resistors. Let me call this A and B. Okay. How about the other one? If we start at B, what do we see? It's connected to the negative end of the 3-volt source. And then it goes to the 20, and then 20 goes back to A. All right, that's how the circuit looks. What do y'all think? Right, everything is in parallel. So just because a circuit is drawn in a different way doesn't mean the connections wouldn't make sense, right? We just have to keep redrawing until it starts making sense to us. Okay, so if you wish to find Req for this, what do we do? Voltage sources are shorted. And my Req is simply these 3 resistors in parallel. So 5.4K. Okay, 5.4K. Make sense? Any questions? Okay. How about Thevenin voltage? Now we are going to apply superposition. Okay. Now we will apply superposition to find the Thevenin voltage. So we'll analyze the circuit and find the open circuit voltage at those terminals with only one source active at a time. And the other source is deactivated, which means the other source is reduced to 0. For a voltage source, it means we replace it with a short circuit. All right, so $30K, $20K, and $10K. And this is my voltage, VOC1. VOC1, okay? This is 20K in parallel with 30K. It's 10K, which would be in series with that one. It's exactly the same as the previous one. Does everybody see that? It's the exact same as the previous one. So we can apply voltage division again, but this time voltage division, the Req is 10K in series with the 20K parallel with 30K. And so VOC1 is given by this. VOC1 or listed as V1. Okay, V1. Does this equation make sense? Let's take a pause while you think over it. Let me know if you have any questions.
I have a question.
Yeah, go ahead.
I'm a bit confused on why did you add 10K ohms to the 30K?
Because they are in series and they are exactly the same as the previous circuit that we saw, let's see, in the previous slide.
Oh,
So
okay.
let's
Like the
see.
combination of those two circuits right there on the slide.
Yes, so it's exactly like this one.
Oh, okay. Okay. I
Yeah.
see it. Okay, thank you.
All right. Okay. Let's see, voltage divider. Yeah. Okay. Any questions? Yeah. It could be. I mean, so the question being asked is, could this be like an audio amplifier? I mean, it's like a generic circuit could be found in multiple different kinds of circuits, or we could come across this kind of circuit in several places.
Wait, sorry, I have one more question. Sorry.
Okay, go ahead.
Why did you
Hold,
multiply
hold on,
by
hold on, hold on. There's in-class question that we are so
okay. my-
sum of all the inputs. Could be yes and no. It depends on how it's connected. Yeah. So yeah, it just depends on how it's connected. All right, online. Yeah, go ahead.
I is the reason we multiply by 2 because it's 2 volts? Is that why we did?
Yes,
Oh, okay.
yes,
Okay, okay. Thank you.
yeah. That's why it's 2 volts. And the circuit, as we see, is symmetrical, right? The circuit is symmetrical. It's a symmetrical circuit, parallel branches, doesn't matter which way we draw them out. So in the first one, we are trying to find for the 2-volt source. In the next one, we're trying to find for the 3-volt source. So all we do is we apply voltage division again. This time, the 2-volt source is shorted out and the 3-volt source is active. The circuit looks different because we are drawing it on the other side, but electrically speaking, there is absolutely no difference. Okay, it's exactly the same. So VOC2, yes, right. Yes, so question being asked is the REQ from the perspective of the source or from the perspective of the output? It is from the perspective of the source because we are applying voltage division to the source voltage. Yeah, good question. This is 20K, this is 10K. So now in our REQ is going to be 20K in series with a 10K in parallel with 30K. Now the REQ is different. This is the REQ from the perspective of the 3-volt source. So the terminals of measurement, terminals of analysis are different. And hence V2 has a different REQ compared to V1. You apply voltage division, multiply by 3, and you get your answer as 0.82. Once you have both V1 and V2 or VOC1 and 2, you have to add them together to have your actual Thevenin voltage. which is 1.91 volts. Okay, and that is superposition. We break up the circuit into multiple pieces. You analyze each piece individually, and then you sum them all up. That's superposition. Now, obviously, it takes a long time, because if you have n number of sources, you have to perform n analyses for each voltage or each current that you want to find. Right? If you have two sources and three resistors in the circuit, and you wish to find the three resistor voltages and the three resistor currents, right? That's 6 quantities. 3 resistor voltages and 3 resistor currents are 6 quantities, and we must analyze the circuit 2 times for each quantity. So 12 separate calculations need to be performed. If you had 3 sources, it would be 3 times 6, 18. 4 sources, 4 times 6, 24. And so you can see how unwieldy and large and laborious it could get. And superposition is very convenient in some ways, but if the sources exceed, like say, if n is greater than 3 or greater than 3, then it becomes a bit too much. Okay. All right. Student exercises. SPICE verification of that circuit. So I'm assigning a student exercise or student practice at home. And the next slide is also a home activity. So it's not homework. You don't have to submit this. This is for your understanding and for your learning. You can work on this by yourself. You can work on this with another friend. You can work on this as part of your group. That is fine. But you need to solve it manually first. So first, try manual solution. And then try LT-SPICE. Okay, first try manual solution, then try LT-SPICE, or then try software. So it's a circuit that has a voltage source and a current source, 3 resistors. But as far as circuits go, it's rather straightforward. So it's not too different. Okay. Remember, voltage sources replaced with a short circuit, current sources replaced with an open. Homework number 2 will be posted sometime later tonight. Won't be due until another next Sunday. Okay, so you have plenty of time. Quiz on Monday will mostly deal with Thevenin Norton concepts and perhaps a small problem. Nothing too big or anything like that, but just application. Students need to understand how to apply the process. That's all. And that's about it. Yeah. Okay. All right. So I'll bid you a good weekend, and I will see you all on Monday.